Welcome back to Large Scale Machine Learning. So we're going to continue our discussion about the overview. So we first need to understand whether or not having more data is necessarily better. So does more data actually improve the ability of the algorithm to learn from the data? So there's actually more ways than one to deal with a large data set. So one of the ways is actually to deal with this large data set by dividing it or subsampling it into a smaller data set. In other words, we throw away some of the data that we don't need, because if you take a representative sample of the data, we may still be able to learn from the characteristics. So for example, if in the previous 150 million rows example, we randomly sample 10,000 rows of data and use that to learn any patterns in the data. 10,000 rows is a fairly reasonable number for a data set. But if there are some rare events, maybe this actually may skip over some of those rare events. So it really depends on data. So if we have data that is well distributed, 10,000 random samples from 150 million will probably be quite representative. The amount of data required depends on the dimensionality of features, how many columns of data that you have, how complex is the relationship. Right, if it's a more complex relationship, typically you will need more data. Higher dimensionality also tends to require more rows of data in order to learn the patterns from it. Otherwise, if you have very many columns of data and you don't have sufficient rows, then you will suffer from the curse of dimensionality, and every row looks unique, so you don't actually the algorithm can't actually discern any meaningful patterns in it. So too many columns of data is not good unless you have proportionally a large number of rows of data. Secondly, if the relationship is very complex, you also need more rows of data in order to understand what that complex nonlinear relationship is. And is there a threshold beyond which having more data actually doesn't actually improve the prediction? So we are talking about having more data, and having more data enables us to learn more complex patterns, able to deal with higher dimensionality data. But is there a limit to how much we can? Is there a learning capacity, right, in your algorithm beyond which, even if you add more rows of data, it's not going to improve the performance of the model that's built from it? So this is a key question that we need to answer in order to understand whether or not we need to deal with a large-scale machine learning. So if the learning algorithm actually cannot handle beyond 10,000 rows of data, it is not very meaningful for you to give it 150 million rows, because it's not going to learn anything extra from those extra data that you pass to it. So one of the methods that we can use to understand whether or not the model performs better with more available data is what we call a learning curve. So there's actually an example in scikit-learn where we can plot the learning curve, which is basically a graphical form of the representation of the performance of the model with different amounts of data. So we want to see whether or not, as you add more data to it, does the performance actually improve. So generally, you should observe that as you add in more data, the performance should be increasing. But beyond a certain limit or threshold, you find that actually adding more data doesn't necessarily improve the performance of your learning algorithm and your model anymore. That's because every single learning algorithm has a learning capacity to it. So it can learn more and more complex patterns, but there's a limit as to how much it can learn if you start giving it more and more data. So let's continue this discussion. The learning curve is a great tool to have in your toolkit, and it's a visualization technique that can see how much our model benefits from adding more training data. It shows the relationship between the training score, which is the measure of how good the model is, and the validation score for your machine learning model against a varying number of training samples. So the one of the axis is actually the number of training samples. So we are basically plotting the performance or the score for the training set and the test set versus different number of training samples. And generally, cross-validation procedure should be taken into effect when plotting the learning curve. So we want to make sure that we don't have, we try to avoid overfitting. So we should do the cross-validation procedure as we're plotting this learning curve. So here's the example of a learning curve. So you can see that in the first row, first column, which is this particular graph, there's basically we are plotting for a naive Bayes classifier using the MNIST digits dataset, and we notice that the training score and the cross-validation score are both not very good at the end, right? So it's just like 85% at the end, and the training score is decreasing, but the cross-validation score is actually increasing, but the training score is decreasing. However, the shape of the curve can be uh, However, the shape of the curve can be found in more complex datasets. This kind of curve can be found in more datasets quite often, and the training score is very high at the beginning and decreases, but as the cross validation score actually improves, okay, it's very low at the beginning and then it improves as you provide more and more data, because it's improving is learning, right? It's becoming less and less overfitted, uh, but the training score drops because it's actually uh, we are actually changing the parameters with more and more samples. In the second one, we find there's more convergence. In this first one, the first row, we see that the learning curve with the support vector machine and RBF, we can clearly see that the training score is still around the maximum value, and the validation score can be increased as you provide in more training samples. So the question is beyond 1,400 training samples. So the x coordinate is basically the amount of training samples, as you can see from the bottom, and the y coordinate is basically the training score given a certain training sample, number of training samples for both the training set as well as the validation set. The training set is the one in red. The cross validation score is the one in green. The question is that, do you think that it will improve even more? And you can see that it's actually improving because the cross validation score is approaching the similar value as the training score. Same for this as well, they're actually approaching, but will it actually approach even more if you increase the number of training samples? So for the second example, we can see that actually beyond like 800 training examples, it doesn't really improve very much anymore. So it sort of reached a saturation point, right? There's no more improvement. So providing more training examples for the second algorithm is not likely to improve the performance very much. Whereas for the first example, maybe there's still a gap and they would actually approach each other even more if you actually increase the number of samples. So first example shows us that we can possibly feed in more data and see what's the performance improvement. Whereas the second one basically has reached a saturation point, and the learning curves indicate that there's very little improvement that we can make by giving it more data. We can do more feature engineering, but just adding more rows of data is not going to make it any better. Just to revisit and reiterate the previous points. So at the very beginning, when we have a very low number of training samples, you can see that there's a big gap between the training score and the cross validation score. This indicates that basically the model is very overfitted because we are basically not having enough examples to generalize the performance from the training data. So there's not enough training samples for us to generalize from it, and hence there's overfitting. But as we increase the number of training samples, you find that the generalization improves and the cross-validation score approaches that of the training score. So the amount of overfitting reduces, and it keeps reducing the more data we actually give it. And towards the end of this learning curves, we actually see there's still a gap. So this suggests to us that actually there may be still some performance that we can act out of it if we actually give it more training samples. And in this case, the conclusion is the learning curve shows that adding more training samples may actually improve the situation. Now for the second curve, similarly, with very few examples, it is really very overfitted. There's a big gap between the training set performance and the validation set, cross-validation score. And as we add in more cross-validation training data, the convergence is there. That means there's less overfitting. And above 800, we can see that actually both of them have really reached a saturation point, and there's not much improvement in the data in the performance of the model beyond 800 training samples. So this shows that it is already converged, and adding more training examples is not going to improve the situation. So there's very little point to add more data and try to improve the model by giving it a larger data set. This doesn't mean that you cannot attempt to try other methods. For example, to not just add more data, but to do some feature engineering. So if you can engineer a more relevant feature, you can basically improve the performance, or you can do hyperparameter tuning to also improve the performance. This graph simply shows you that if you just hope to get better results by just getting more training data and adding more training data, this is not the way to go, because your performance has sort of saturated at 800 samples. So just adding more training data alone is not going to actually improve it for this particular situation. But for the first one, yes, you may still get some performance improvement. So in the case of underfitted model or high bias underfitting, adding more data alone won't help. So if it's already underfitted, that means your assumptions, your hyperparameters in the model do not actually fit the actual situation of the data, shape of the data. Just adding more data alone is not going to improve it. So you can see that in this case, the performance started off very poor. The training set example, the red one, is quite poor, and so is the validation set. And although they converge, they actually still remain at a very low level. And adding more data doesn't actually make it go up, right? The performance is always sort of below 50%, even as you add in more data. When the cross-validation and also the training scores, they converge, but they remain very high, that means below 50% or 0.5. No matter how much data we feed into the model cannot represent the underlying relationship and has a high systematic error. Think about this. The model is actually supposed to be non-linear, but you assume that we can fit a straight line to it. So if that's the situation, there's no amount of parameter tuning that you can make to a straight line to make it a curve. So if you are making an underlying assumption that's too simplistic, or the model is basically too simplistic for the data, adding more data alone is not going to improve. So we're still going to get poor fit and poor generalization. So how can we improve this? So as you know, underfitting basically means that the model is too simplistic or too simple. So we need to change the bias and variance trade-off by increasing the complexity of the model. We can do that by engineering more features, or we can change the algorithm, or we can try to adjust some of the hyperparameters by maybe introducing some sort of kernel, RBF kernel, for those algorithms that allow for it, such as support vector machines, so that it can then fit into the pattern that's actually in the data. So these learning curves are quite useful. They can show you overfitting and how it changes with more data. It also can show you the pattern that you normally encounter in the case of underfitted model, right? Like this. So when you see this kind of pattern, just remember that there's no point adding more data, because that's not going to improve it. No matter, it doesn't matter if you add in 1,000, 900, or even 10,000. It's just going to remain flat at this low level, low value. So the opposite scenario, overfitting, can also be shown in the learning curve. So in this case, it's high variance or overfitting. So this shows us that actually we probably need more data, or we need to do some simplification of the model in order to adjust the bias variance trade-off. So you can see that at the very beginning, when we have not enough examples or training samples, definitely there's overfitted, and it's actually improving as we add in more data. So it does show us that probably we need to add in substantially more data, like maybe 10,000 rows of data, so that this curve actually approaches the cross validation score actually approaches the training score. Or we need to actually do some adjustment to the model, tune hyperparameters, maybe introduce a regularization, or simplify the model by doing feature selection and dropping some of the unnecessary or redundant features. So here you can see this characteristic is quite different from the previous one for underfitting. There's a big gap between the two, but it is actually becoming narrower. The gap is narrower as you add in more data. So it suggests that we can add in more data to make it even closer, or we can do some changes to the algorithm. There's a gap between the two, and we require more data to improve, or we can try to simplify the model, drop some unnecessary features so that the model complexity drops, and therefore, in accordance to the bias variance trade-off, when the model complexity is lower, and will originate in the overfitting region, reducing the model complexity will actually bring it into the right fitting region. So you can see that the learning curve is quite useful. We can actually diagnose various types of situations. So here's a quick quiz. The purpose of the learning curve is to what? A. Tune hyperparameters. B. Show if more data could actually improve the model fit. C. Detect overfitting. D. Parallelize the execution of the model. Or E. Increase the speed of training. So you should pause the video for a while and think of the answer before proceeding. Here's the second question. The learning curve in the figure below, which is this figure, indicates what? A. Right fit. B. Underfitting. C. Overfitting. Or D. Too much data is available. Too much training data is available. So you should pause and then think of the answer before moving on to the end of the video. And with that, we come to the end of this set of slides. Thank you for your attention, and I'll see you in the next set of videos.